एक बार प्रेस कर दो। ना प्रेस मतलब वो टॉगल।
We'll just go through the input file and look at some of the fields and features that are there.
Dilute दो पहले. Dilute दो. What are the overview features that you have added? In file is one.
Yeah, that is what we'll go through now.
Yeah, so.
Okay. So this time for the grand functional API model, the most significant thing I think we have changed is to rename it to grand functional API. So this is shorter. Next, we have added a feature for dynamic input files. So just like in Auto, when you are running a simulation and you are in the middle of your simulation run, and let's say you want to change a fundamental constant, let's say constant in the value, constant in your model, you can go and change the input file, which will in turn change the constant in your simulation. So this allows you to do, let's say, systems like also synthetic simulations, but also replicate experimental conditions much more accurately, because now you can change certain conditions you can do. So one of the things that we have added that you can change, which is useful, is the part field composition. So for directional circulation systems, the part field composition plays a role in the microstructure that it forms and the segregation that happens. And to replicate experimental conditions,
you can draw and show it.
And draw and show it.
In the column. In the pocket.
It's very formal.
You are wearing a shirt that's already formal.
Yes. Okay, so let's say this is your configuration file. Okay. Now this is your domain boundary. This is where your simulation is. So this is your simulation box. Now, depending on the interface velocity and the given diffusivity, you have a diffusion length. The diffusion length will be somewhere around here. For slow like Brisbane light simulation, the diffusion length will be somewhere around here. So first, what we do is we can only impose boundary conditions in these cells. So there are 3 boundary cells in which you can impose these boundary conditions. So if I want to change my particle composition here, I'll have to interpolate it and change it here, which is now in the input file called EIDD, exponentially interpolated Dirichlet, but we can find a better name for it.
Okay, wait, he has given away. Wait. One section. So typically you have the decaying diffusion length very far away. Right? So that if you want to do very slow magnification, you typically then have to use very large boxes. Right? So what he has done first is to impose a new boundary condition, as he is drawing now, where you impose the condition on a finite box, but the composite condition over here will be such that it will mimic the particle far away. So it's not like an infinite boundary condition where you are seeing the far field much farther away. So effectively, you can reduce your box size length to a much smaller.
So if you don't do it this way, what happens is a very minor 1e minus 5 change in the composition variable here in your domain will cause changes in your microstructure here. So to make a 1e minus 5 change here, we have to interpolate it and make the change correspondingly calculated here.
And this is done because in the far field composition, it is typically a 1D composition. The perturbations of the microstructure, which are spatially relevant and near the microstructure, are not so that far away it's nearly 1D. So you can use the 1D diffusion profile that you typically have, steady state diffusion profile, for this approximation. Right? So it essentially allows you to reduce expensive calculations to.
It allows you to reduce your box size and allows you to do realistic calculations. So that is exponentially interpolated Dirichlet. Now, because we have control over the particle composition and we have dynamic input file by which you can change the values at runtime, we can change this particle composition at runtime. So what this mimics is experimentally if you
No,
in situations that you know these experiments also mentioned, right? Even
So because of this, what you can now start to do is, let's say, in your phase diagram, there are a variety of far-field compositions that where you get couple growth or some type of microstructure formation. And in experiments, typically you will do one experiment to figure out what the microstructures are, right? But in a simulation strategy, what you can think of doing is to span all of those compositions in one single run. So the idea is we will keep changing the far-field composition as a function of time as you please, and then as that changes, you also track how the microstructure. All of that is happening in a single simulation run. So what you essentially will have at the end of the day, of the entire composition space, what is the microstructure space as well in one single run. Okay, so that freedom comes out as we will demonstrate it here. Just demonstrate it in your video. That's
so there are two things you can do. If you have a phase diagram, you can linearly change from one composition to other. That you can do for any phase diagram, like how like multi-component phase diagram. Also, in a ternary phase diagram, you can start at the center and you can spiral through. That is what we found was like good enough for traversing part in the composition space. So this is controlled by here. EIDT mode 1 is the straight line, and EIDT mode 2 is the second one. And the composition partition is also dynamic. It means if at runtime you want to change the particle composition by hand, you can change it by hand. And this sort of changes the microstructure. The step 0 is just for when do this start.
So what you mean by dynamic is now as slightly different from what you did in your both hands-on videos, hands-on tutorial. The in file is not static anymore. Let's say the in file is put into the solver and the text file is there in that folder. You can actually change the in file while you are running the simulation, and the changes in the in file will get reflected in the simulation. Okay. So that is what he means. So you don't need to stop your simulation and restart anymore. Keep continuing your simulation as you change the text file. So as soon as it reads that there is a change in the in file, it will affect those changing parameters.
Okay. So this is a three-phase reflecting, and on the right-hand side of the plot is our composition plot in the direction of growth. So this is where the cultivation front is, which we see from the top view. And on the right hand side, this is almost the end of your box, and beyond that is your particle composition. So we want to essentially change that particle composition linearly towards this yellow phase, right? Yeah. So as you change the particle composition towards the yellow phase, the volume fraction changes. That is one of the effects that happens, and you get different patterns. At some point this dies and you are out of your simulation box, only command units. So this is one of the new things you can do to span the composition space. This also helps you to identify experimental microstructures. So if you see something experimentally, whether it relates to under what condition does it happen, you can study that. We'll show one more for
Shish kebab.
Yeah. So this is where we spiral through the ternary phase diagram. It just leads to changing volume fraction, and you can see the interfaces do not stay static. For a particular far-field composition, the interface shapes are different. So this splitting of the decombination. This is
This is
Phase field.
phase field.
This is composition. Yeah.
This as you change the composition,
Composition, how will it be? And this doesn't have elasticity,
this is solidification.
solidification.
You can do that coupled with elasticity also, as a really matter.
There's no strain developed.
No.
So this is one of the things you can do. One more thing you can do is that is in the include file is the surface anisotropy. So we have added two new anisotropy modules in which earlier we had only four-fold anisotropy and isotropic conditions. Now you have two-fold anisotropy about any axis that you want, and there is one four-fold anisotropy about the growth direction, but that can be rotated. So it's like so for systems in which exhibit two-fold anisotropy, you can orient it and then show it.
Wait, no. So what typically was there before if you just open your eutectic microstructure once, I'll tell you what the reason we did this. This is one of those points. Maybe the static picture. The one that was read. So, for example, here, crystallographically, there is a what is referred to as orientation relationship between this phase and this, which means the planes of this and the planes of this typically are oriented as well. Similarly, there could be orientation relationship between this and this. Now, this sets the interface character of this and the interface character. And they essentially can have, in principle, different types of anisotropic. And the anisotropic formulation of this and the anisotropic formulation. So, what we have introduced now, previously in the code, we could have only one anisotropic formulation. We now have interface specific anisotropic formulations, which means we have set of anisotropic functions separately done, and we can associate which interface what anisotropic function we have. So for example, I can say here I want 2 anisotropic. Here I want 4 anisotropic. So this feature has been added into our module, making it you actually simulate multi-phase, multiple interfaces and any other.
The starting point of
Okay, so here what we have done is we have started from a uniform configuration, and then we have found the equilibrium microstructure. And once we have found the equilibrium microstructure, only then we have started varying the phase with parting composition. So this is not a filling state. So the variation in
so you can show the matrix. You can show how you are doing the association of the anisotropic.
Yeah. So earlier we had this parameter called DAB, which was the anisotropic strength. And now we have a parameter called FAB, which is the anisotropic function mode. So if you have 4.2 means that it's twofold around y-axis. It could have been a better name, but this is fine. And twofold means it's twofold. And if you want fourfold, you're going to put fourfold. So for the 0-1 interface, which is the red-blue interface, you have 4.2, which means it's fourfold around the growth direction. For the 1-2 interface, which is yellow and blue, you have twofold around the y-axis, which means these vertical, the horizontal lines are most stable. So now we will sort of try to see the effect of different anisotropic functions in a given eutectic. So initially we start our system from a random state, not random state, like uniform state. So what we want is we don't want any of the stable interfaces in our system. So what we will do is we'll tilt our anisotropic functions so that it's the slanted interfaces which are stable. You can get this by tilting your rotation. You can tilt by fourfold rotation to 45 degrees. No, without tilting the rotation to 50 degrees. So you get a microstructure which is like this. So now at some point we want to revert back to the original fourfold microstructure, in which we will see how a eutectic pattern develops. Sort of, you can see how the symmetry breaks and how the stable interfaces form.
So this essentially shows you how strong anisotropic effects are in simulations. It rides over any other effect.
So you get your stable state on. Yeah.
This happens.
At the eutectic, near the eutectic.
So if you
Very fast phenomenon.
Yeah, this reorganization as we see here is of the time scale of some microsecond. Okay, very fast.
so because blue and yellow were twofold, you can see that they are nicely staggered twofold, and red and blue were fourfold. So they're still following that. There are multiple stable states. It depends also on the initial condition, but the brick-like structure that you get is possible.
So this structure, by the way, is seen in experiments. Routine in experiments, you mostly have this structure.
Fourfold people realize
Yeah.
check this in.
You can just draw what you mean by twofold and
Can happen in solid state
also. So you can, in principle, the degree of freedom we have provided is any interface, you can provide a functional form to it, and you can describe its anisotropy independently of any other.
So your anisotropic function, which sort of determines the wool shape, is let's say for twofold is something like this. This is a high energy sort of orientation. This is a lower energy orientation, right? For twofold it is so, and here this is x and z, and this direction is x, y.
Y is the group.
Y is yeah. So inside the plane is y. So for fourfold, your residual functions look like this. So then you get the equilibrium rule shape, which is like this, and that's right.
Inner envelope. Inner envelope. Inner envelope.
Oh yes. Yes. So that is twofold, this is fourfold. And nearly in 3D, you have a low coming here for the proper fourfold one. In the 4.2, this orientation is isotropic. Only on the planar mode you have anisotropy.
So 4.2 have anisotropy in the XZ plane, and growth direction you have isotropy.
Yeah.
So if you see any change in interface fluid direction.
So this is in the regime where we do the asymptotic connection. Even if you have interface bit change, you will still rectify the same property.
The properties.
So we also added the flow module. This is the relation that you have seen. So this is controlled via the input parameters here, which are LBM variables. So you return LBM from 0 to 1, just like elasticity, you return LBM on. You have to give mu, which is one of them is viscosity, and the other is the nu that goes into the LBM part. So there's the nu in the LBM equations. Rho is typically the density, which is normalized, and beta c is the coupling between composition and the velocity. Gy is gravity, W naught is a speed, it's Cs square. In the LBM equations, it comes as speed of sound square, which kind of sets the scale for your velocities. And delta T is the relaxation time for LBM solid.
So the two types of effects are included here: shrinkage velocity, shrinkage flow, and buoyancy flow. These are added in.
Honestly, this. Yes. We also have added in. Yeah. So there are boundaries. The reducing condition for boundary stresses is available with the elastic solver for the green tree.
So you can now, in the previous elastic solver that we had in the GP module, we could not apply. We did not have applied stress effects. Applied stress. Here now you have applied stress effects. So this is now you can do rafting.
Applied stress means you give a displacement.
Yes. So you find the effective displacement for having that applied stress, and you impose that strain, and then solve it.
Loaded system.
Loaded system. Yes. So the entire RVE is seeing the applied stress homogeneously. This is the CMSX4 alloy, which is rafting essentially. We have negative misfit. So the stress is applied in the horizontal direction, and you have elongation of the variance in the vertical. So this is there in both 2D and 3D. So you can do plane.
One more.
We'll add a manual also for this thing.
Yeah, we will be
Explaining
Yes.
what is the spirit of the problem.
So we have one more addition in function f. The type of thermodynamic calculations we want to do is function f equal to 6. So in function.
So if this is a new function added, this allows us to do, when you put a temperature gradient in the problem, typically because C is a function of mu and T, what will happen is that the composition will essentially, or the chemical potential will change in the far field as a result of that temperature change if the coefficients of the free energy in the liquid are functions of temperature. Now, some of it is an artifact. You don't want the composition to change in the far field because there is no composition change. So what we have done to limit this is the coefficients of the liquid are taken as a reference point, just as we do in the F1. They are independent of temperature, and all the temperature dependence is built into the solid. So then you don't have that composition variation as a function of temperature gradient information, making simulations much more realistic. So function F6 is particularly for simulations where you do non-isothermal, okay, where you have temperature gradient.
Directional specification.
One more just a small flag is the invert matrix inversion using GSL. Earlier for the dmu by dc matrix, we have invert to solve for the Cavillion potential.
So remember you had that matrix inversion term to get them use the important calculation. So previously we were using our own routines. There is now a flag to possibly use the GSL routine if you are not wanting to use our routine. We have not found much difference between the two routines. But
So
still,
because maybe the component improvement was 2%, but for it will show as 11 components out there. We have not
I
provided.
don't expect it but too much, but still, if you want it, you can just revert to the GSL interpolation, GSL matrix inversion. There's a flag that you can use. और कौन से keys dynamic है बता दें?
Okay, the dynamic. Okay, so not all keys are dynamic because.
So for example, it doesn't make sense to have a non-elastic calculation and suddenly switch on elastic. That's a useless simulation. You don't want to do such simulation. There are only certain keys which you can make dynamic, or which we have kept dynamic, which makes sense. So for example, you're doing a directional solidification simulation, and you can do a velocity jump currently. Because experimentally also you can do the same. You are doing that crystal velocity at a given point, and you can do a jump and see the effect of the jump on the microstructure. So that you can mimic in the.
Also, to traverse the parameter space, we have made a diffusion of the components dynamic. We have made the bar.
You can change dynamic, so you can impose those oscillations through the inside.
Yeah,
So that is automatic. Reprocess that after this.
So basically, what you can do to have a set of infiles, and the infile can get changed through a Python script, and that Python script will keep changing the infile at periodic intervals of time. That will get reflected in the simulation. So that essentially is great.
So the dynamic inputs are diffusivity. You have anisotropic strength and function anisotropic both. In the runtime, you can change the function anisotropic, which you have just seen. You can also change the rotations of the rotations of the anisotropic functions. You can also change shift. This fine in temperature gradient, you can change delta T and velocity. So you can effectively control your temperature gradient and the cooling velocity that you are imposing. In isothermal simulations, the equilibrium, the T, which is the isothermal solidification temperature, system temperature is also dynamic, in which can do multiple effects such as change of undercooling or going.
So basically, the cooling rate can be imposed. So if you can change the temperature, isothermal temperature, the cooling rate you can.
The thermodynamic parameters are not dynamic, but the particle composition dynamicity is handled by this EIDP mode. And in LVM, the delta T and gravity are dynamic.
Let's go to your question once. The folder.
Folder.
No, folder. Yes, you have already. Yeah, so these are the set of new features. It's already uploaded, I guess. So it's available on the GitHub branch. This is a part of the new. Oh, filling. Yeah. So there's a lot of new filling functions. Particularly in our old solvers, we could not fill the last phase because what the argument was that you fill the solid phases on the n-1 phases, the last phase gets automatically filled up. Okay. So what we have done is added new functions now where you can explicitly fill the last phase. This is particularly useful for precipitation simulations. Let's say you want to have a Voronoi grain structure made up of the first few phases, and you want to now fill up the last phase, which could be a precipitate phase, right? And see it grow. So this is essentially like an austenite-ferrite problem. You have ferrite growing or austenite grain growing in a ferrite matrix. This you can do. So the filling functions, cylinder, cube, sphere, random cylinder, random sphere, these 5 functions have been modified or added such that you can fill up the last phase.
They don't, the volume just don't do here.
No. It's all of that is fine. Previously, the algorithm was that you fill only the in the n phases, fill only the n-5 phases. The rest of the region will get filled up by the last phase. So you could not fill up the last phase because of explicit.
There was no.
But now you can fill up the last phase. Yes,
For this class of problem, you invoke this. If your phase transformation, you are summarizing volume change.
Volume change is something we can do only in the flow problem through a change. We have not used because strain effects we have not. We can do it through the eigenstrain. You can effectively choose the volumetric eigenstrain of the phase transformation and impose that volumetric.
But then something like the solidification, it should not get.
It's not a problem.
We added a contents that you can now fill up the choice.
What is that?
Yeah, contents that in the last phase as
Because let's say we are doing the austenite ferrite problem. Let's say austenite, you are doing heat treatment. You are having, let's say, ferrite in austenite line, or the reverse. You're going above, you are having the austenite getting in a ferrite. So first phase and last phase, you should fill up depending on what is there, what is the microstructure you want to see here. So here, therefore, the last phase can be filled up. You can do a Voronoi of the last Voronoi of the grains that you want and fill up whatever phase is going to grow as small precipitates, and these will grow. Nucleation. So you can essentially have a nucleation of austenite in a ferrite matrix and see it.
Earlier also you would have been able to achieve that, but the way you would achieve that is to write with many fill functions that did the same thing to effectively fill the last phase, but now you can just fill the last. It's a simplification of your code. And automatic ambient decomposition. You need not do the 2x2 at the end.
So that is he has added. You don't need to do the 2x2. You can do it. If you don't do it, it will find some optimal way of doing it and decompose the thing automatically. 2x2 or 2x2 or whatever. Anything.
So talking about the GP Ambex updates. So we've added precipitation. So you can do precipitation with and without elasticity. So I'll just run through a few simulations. We saw yesterday. Now within this you can add multiple components, multiple features as well. One. As you can see, I have simulated 3-phase NILM here. Also, the elastic parameter we are making it, and this is 4-phase NILM model. Next, something that we have ready, but we'll add it within a week. Mostly will add it. It's the grain growth. Few tests are remaining. So once they are done, we'll just add this in the model as well. So here you can give as many grains as you want to gain a multiple distribution. So in grain growth, you assign multiple tests.
These are all multi-phase parameters, multi-order parameters. So there is the orientation feed thing also, but that is there in the open form model. So there you can do growth also with that. Okay, so we have two. We have done that. So there is a formulation from Mathis that we have implemented, which takes care of that pinning problem that you have.
You also take care of that.
No, this is multi-order parameter. That is not there in this.
Apart from the single level solver, we've also added multi-level solver. So as you can see, the next image, where we can see that boxes are being formed, the definition going. So these are the updates that we've added for Ambex in the.
I'll be showing some answer that I work in Ambex Lab. So now, as Sir explained, this presentation is regarding National Supercomputing Mission. So this one just a small motivation. So generally in turbines we need plates which are like highly resistant to deformation at high temperatures. So these kind of things are manufactured in Bridgman setup. So as we know in Bridgman setup, there will be a crucible which will be pulled slowly. So Bridgman setup is generally used for casting kind of complicated structure like blades. So we can see this blade which are very complicated structure. And it is generally casted in this where the crucible like this is pulled with a particular velocity, the fixed velocity in a furnace. So this furnace will be hot above the baffle, and below it, it will be a heat sink. So it can be left out to the air, or it can also be another heater which is of lower temperature. So this one from this kind of setup, we can get nice kind of directional solidification. This is from our lab colleagues who have done this EBSD mapping and also this pole diagram of this directional solidification. What is the orientation of the crystals they have shown. So it shows perfectly like it's all oriented in one direction. So it's along the Z direction. So right now, for modeling this kind of directional solidification in the Bridgman setup, we have come up with a model. So this model is what effectively is there in the MicroSim, whatever which is released. So this model is based on the transfer equation. So this is the main equation, the transfer equation. As you all know, there is like diffusion term, which is this, which we have been seeing, and there is a driving force, okay, which is based on the enthalpy, and this is latent heat, LH is latent heat, and the phi is this one is the term where the heat storage is. So it's specific heat and also the density and the change in temperature. So this phi, whatever is there, this is like modeled using this kind of function. This function is based on the temperature of the material. So if the temperature is below the melting point temperature, it is solid. If it is above it, it will remain as a liquid. So this is the error function. So it will be like 1 in the positive x, and it will be negative. Sorry, it will be 0 in the negative. And these things we put into the heat transfer equation, and this is what is effectively solved in the model. So the problem with Bridgman solver is the boundary conditions are quite complex. They are time based. You see this graph which I am showing. So if you start here, the top part is colored in the golden color, and the bottom is fixed. So if you see, it is varying with the time. The span of it is varying with time. So this to handle such kind of boundary conditions, we use smoother boundary method. So in smoother boundary method, what we do is we simplify the equation which I showed earlier in such a way that it is easy to handle both the Normal boundary condition, which is the convection, and also the constant temperature which is there in the heat source. So that is the very boundary condition. So what we do is we just do the minor modifications to the equation in such a way that we don't need to impose it explicitly. It is already present in the equation. If you see this final equation, there are two terms. One term is related to the constant temperature term, which is related to the heat sources above, hot zone, and the bottom one is related to the convection. So both terms are taken there. Here, if you see this HF is there, right? That is heaviside function, which tells you at what particular point there is a division between hot zone and cold zone. So it tells you the work.
Can you just note them?
Yeah, that's a very nice method. Just this allows you to take this smooth boundary method is a very useful method, particularly where interfaces are you want to employ boundary conditions, but chaotic boundary conditions or complex geometries.
So can you continue?
In your expression, where was velocity sitting? I was trying to see.
It will come in the Heaviside function. The Heaviside function changes as a function of time. So the position at which you apply the directly boundary condition and minor changes with time.
Yeah, here if you see. That is decided by HF, the division.
No, not expression. He's telling that the position
Position which is changing, right?
that's decides the Heaviside.
Like multiplication is there, takes care of this. Multiplication. Here it is.
Oh,
Here it's 1 minus. So that takes. So next is this is like the flow of the work which is happening in the generally what we simulate in open flow. So it is normal what we do in finite element grid. Into that we will import geometry and we'll define the lattices which are close to the regions where we want to concentrate, like what we saw in dynamics also. Then afterwards, what we do is we smoothen some of the fields to the simulation. So I will get to that part. So that is called domain parameter. It is effectively what it does is it will specify the area in which you want to solve your equations. So that is domain parameter. That is smoothened down. And Based on that only, we can use the boundary conditions. We can set up the boundary condition. Then the other thing is the thermal equation is solved.
Yes.
Most of it, only thing is we have to write the equation and also the smoothly. So these are some of the simulations which I have done in OpenCode. So this is the 3D simulation. I'll show you the 3D view of this also. This is effectively 200 plus 200 into 1000 lattices surface. So we can take in millions the lattices, and the simulation had to run for at least what to say, you can see the time like 700 seconds or so. It takes days to run, but this is one of the first simulations we have. This is a 3D simulation. So effectively, you can clearly see the directional solidification of the solving, and we can see also the temperature. And it is going to come down in the cold zone. So this, and these are the parameters which I have used for CMS. And so this is the isometric view of this interface, the solid liquid interface. Visible. So you can see its topology changes as the simulation goes on. And from this we can come to, and also we can also come to know the thermal gradients and all we can map using this, which is very important for microstructural properties of the alloy, whatever is getting solid. So another thing which we have done is parametric analysis, in which we change the horizontal temperature and we try to see how the interface is going to evolve. And we have seen, like, if you increase the temperature, the interface is not going to travel as fast, and it's the change of it from concave to convex shape is also going to be delayed. So this is one of the parametric analysis which we have done, and this is done in 2D, not 3D. And these are some of the gradients at the interface which you get from our simulation. And we see that gradient, which is so you can see these three curves. So these three curves are representing three different horizontal temperatures. These three different simulations. We see that the gradients at which the gradient signature is different in different simulations.
So what this diffuse interface type of activity allows us to do is to put in codes, for example, inside the material. So the codes will be essentially allowing you to do hollow castings, and that hollow casting can be simulated in one single go. It's only possible because of the diffuse way of putting down things. The boundary conditions become rather. Yeah, it's okay. You missed it. That's why. Don't need to go back. That's fine.
So another thing which we have done is we also could control the interface, how it is going to evolve by controlling the temperature, the horizontal temperature using PID control. So it was whatever the parameters which are used in PID was obtained using Ziegler's criteria, Ziegler's method. So it is a heuristic method. But from using this, what we could achieve is, during the directional solidification, the interface was kept flat instead of it being concave or convex. So as the simulation proceeds, the temperature was increased, as I show you in the next slide. So the temperature was increased gradually in PID control in such a way that the interface more or less remains flat throughout the simulation.
So the challenge in a segment is, when you start the solidification, majority of your crucible is in the hot zone, and very small thing is in the cold zone. You typically have a hot zone dominated situation. So your solidification contour of the isotherm will be shaped like this, concave down. As you start going into the cold zone, because you start to have a situation that you are becoming more and more cold dominated. So your shape of the interface will become concave upwards. And this is natural, you cannot assume. So, but it has consequences on how you grow the grains. Because if you are a shape like this, the grains would like to diverge downwards. If you're shaped like this, the grains would like to go like this. So now if you want to have things like single crystal castings, this is not good. You would like to have situations where the thing remains nearly flat. So what he has done is to come out with a control law through simulations. Because in the simulations, you can track the shape of the interface. And depending on the shape of the interface, you can take a decision whether to change the hot zone temperature or not. And if it is, change the hot zone temperature such that you make it flat. And that's what the PID control he is talking about. This PID control, Paparazzi people are actually doing it from long years ago. In Bridgman, nobody does it. And we thought of doing it in the simulation because you can actually track the shape of the interface in the simulation. And this control law of how you need to heat up the temperature furnace can then be passed on to the actual experimentalist, and he can test it out on his furnace. That is the advantage.
And the last thing I wanted to show was the blade simulation. So given the showing the cells here, this blade is quite complicated. So we were able to do this. So this one, if you see, this is the temperature and also the solidification we are showing. So this look.
It is investment casting. So you put in the casting in the shape itself. The mold.
There.
So this kind of casting also is a little bit complicated than the capture using.
So the module that will be uploaded, you can actually do non-trivial geometries of the stone. You can put in meshing, all of that workflow will be put in. So you can.
FDM.
This is FVM, finite volume.
Last period.
That's what we do with the smooth boundary formulation, no? So it's like a shape that is given by that function. And once I put that function using the job meshing that I have done, I didn't need to take care of the boundary condition. It's part of the governing equation. So that is what the advantage is.
The main parameter will tell you the shape, in what shape you are solving. So that parameter, if you properly map into the mesh, you will be able to get this shape. And there you smoothen it out, and afterwards you can evolve your temperature. That's what we are doing. Then these are gradients which we obtain from our simulations. So around the interface we were showing how and also along the transverse plane also how the gradients are going to be distributed. We were able to capture from our simulations.
And previously, there's no open source solutions for these. And the only commercial solutions are Procast. And these are extremely costly softwares and closed softwares. So that was the motivation for developing the open source modules.
Last one is so these are my future dimensions. So I wanted to have so realistic geometries and also seeding technique. I want to also involve in these solutions. Can you choose the orientation of the?
So the point is, it is not coupled with a CA model for the grain selection. But this guy is working on a DNN model, with which we'll be able to simulate the thermal histories that we are going to. So there's dynamic meshing possibility in OpenFOAM, which allows you to do the same thing that we saw in Amrex yesterday. And he has done dynamic meshing with respect to the temperature field. So that allows it to.
Wherever the interface is there will be in our just like what. But we don't use gradients here. I directly use this pipe.
Okay. So this will be uploaded as well onto OpenFOAM. The additive module is present. Once my student Sapnan's thesis is out and he's defended it, we will put it out on.
So for AKS of the CUDA MPI module, we have some new features which are from the filling methods. We have implemented that Voronoi tessellations with which grain result can be done, and as well as this is the Voronoi tessellation which can be used to simulate grain growth, as well as this cube pattern has also been implemented, which can be another method can be used for filling. So apart from this thing, we have implemented HDFI output, which data can be stored parallelly, as opposed to VDK output, which was there in our last release. These are
it is now CUDA MP is working on multiple ports.
Yeah.
So that was not there in the previous version. So that is new. You're able to run with MPI on multiple nodes, right? So you have pushed it already?
So I'm currently working in physical programming to develop a case-built model based on implementations. So I would like to introduce you to the simple parallel programming method. C is nothing but a higher level abstraction of C++. it should allow you to run your simulations in GPUs or FPGAs. So, what is the need of such a parallel planning? Let me show you a stat, please. This is from top 500 website, which will showcase the top 500 supercomputers all along the world. The top 10 supercomputers. You can see that the first one is AMD. The second one is also an AMD. Second one also uses an AMD accelerator. Third one is based on a Intel data center GPU. The fourth one comes with an NVIDIA A100 GPU. So initially, the programming is based on CPUs. So when NVIDIA opens their GPUs for parallel programming using CUDA, so then it all starts to people start using accelerator like GPUs, general purpose GPUs for programming their models. After almost 20 years, NVIDIA was doing a monopoly on that. So now you can see that that monopoly is almost over. The top 5 10 it's only on 4 data center which uses NVIDIA GPUs. The rest uses AMD and Intel GPUs as accelerator. So, as a programmer or who develops a program to run a program for a physics-based simulations, now it is almost necessary to write the program in such a manner that we can run it on vendor-independent architectures. So, SQL is such a tool where we can run our simulation independent of accelerators, independent of vendors. So here I will just give a brief overview of what is SQL. SQL is a C++ programming method for heterogeneous parallel computing. It's an abstraction layer that enables our code to run on any devices, irrespective of the vendor. CPU, GPUs, or FPGAs, whichever is available. If we have a GPU or FPGA, we can offload our work to such accelerator. Otherwise, if it is not available, we can run it on CPUs. It minimal change the code. That is the advantage of CPU. SQL provides to. So the specification for the SQL is maintained by Kronos. This is their website. If you go through the website, you will get some understanding of what it is. And the main source to start programming on SQL or start learning SQL is this particular textbook, which is openly available. You can download it and start learning SQL. Other than that, the one other important thing that I would like to talk with you is this Unified Acceleration Foundation, where people develop libraries. It is independent of vendors. So they have developed one. So there are 188 versions available from this developed by Unified Acceleration Foundations. They can run in AMD CPUs as well as Intel CPUs. They have developed one math library which can do math operations in CUDA, AMD, CUDA CU+, ROC+, and also for Intel NKL library. So it will use vendor provided libraries to offload the work, which can make our code faster in GPUs. And Intel also developed a one API actually Intel will start developing on something called DB++, which later taken care by later people, later others.
So this is for only C plus.
Actually, C is based on C++. It is an abstraction of C++. So the advantage is that the way that we use a C++ code, we can follow the same routine SQL follows. With minimal changes, we can offload the work. So usually writing a code like once we will write it in serial and then parallelizing. But now it is like when we write at the time itself, we can parallelize it. We can think parallel. That is the advantage of SQL.
Now SQL also has a Python binder module.
Python binder is also available. It means Python also you can, like for machine learning, AI accelerations, we can use SQL function. And SQL now more companies have started using SQL such that even we can do run the programs in our Samsung mobiles. They have a processor. Some modules available in Samsung phones which allow us to run our programs in mobiles. I think it's available in the yeah, I read that news in this topic only. I will go through the example code that I have run.
Control plus, can you do? Control plus.
Open fields.
Check.
So I have a small program based on arithmetic equations in simple that I will just demonstrate you.
Have this as example.
Example. He'll upload that as example.
These example codes are available in a GitHub repository.
No. Upload it in our repository, MicroSim. Put a folder, example code, and upload it there. So people are able to follow the future development.
We'll do it later after the presentation. Not today, we can do after.
No, not now. After the presentation.
This is an example program I will walk through. So I'm not going too much into the arithmetic equations that we have covered already. So this is a equation. So this is the first one. We have to select a queue, which is a communication with the device and the host. You can select a queue with the queue selector. You can see this particular line of code, which will select the device. Yes, it has a queue.
In the font size can increase. Maybe you can close the terminal below. Use it later.
So here we will select the device. If you want to change this CPU to GPU, the only thing that you have to do is to change the C to G. So then the code will start running in GPUs. Same kernel will start running in GPUs.
It is treating the CPU as an accelerator.
Yes.
So this is just one thing. So this CPU, when it is using the CPU, is it doing threaded parallelization or MPI parallelization?
It's a batch parallelization, kind of an open MP.
Open MP, right? So if I want to still use a MPI type of parallelization, what will I need to do to the code?
So that currently we can use a multiple compiler for that.
But it will the functionality with respect to CPU, GPU be the same like this, or multiple changes have to be done?
No,
So if I want to do MPI parallelization,
For multi-node.
multi-node, multi-CPU, multi-GPU.
Yeah, for multi-node, there is a wrapper for the ICPH compiler, which is the physical compiler, which is API ICPH.
Okay.
So which will allow us to run the GPU program, GPUs to run concurrently in multiple nodes.
Okay.
Which will take care of the MPI communication, but that we have to do the same.
And what happens if that thing is different from the CPU MPI, right? If I have to do the MPI on the CPU, will it be handled in a similar way? Same way. I would essentially like to see how simple it is to do that particular thing. So this I understand. This is a threaded parallelization. This should be managed in the same way. But it's the MPI thing where I think there'll be difference. Will there be a difference in the way you start? Because in the GPU you have things of computing, sending information, which could be NVLink or shared memory type of activity. Whereas in the CPU, you have to access InfiniBand and do it slightly differently. So that architecture, I would like to see how similar they are.
Sir, this node, it will
Single node I'm not worried about.
the what threads available in the same
Not threads,
processor,
MPI.
same what threads available in the process is taken is not is collectively taking as a device.
Yeah.
And the inter-node communication will happen through MPA.
I understand. In one node, there is absolutely no problem in my understanding. Multi-node, when you have to access the InfiniBand, the way you access the InfiniBand cannot be the same for the GPU and the CPU. Because the GPUs don't know the InfiniBand. It has to happen through the CPU and then through the CPU.
No, if we just instead of importing OpenMP, we can import the MPI from within the one API provider.
I understand.
Now in the ICPH compiler, we have to specify this is a GPU code. We are compiling it for CUDA. We have these nodes as
What I'm saying is this cannot be that simple one-line code difference.
No, there is MPI on top of it. We have to do MPI initialize, MPI send the Yeah.
No, but I'm pretty sure this cannot be that simple because the architecture is. So same type of data I look up in C. We are all not I'm saying not always solved it. MPI inter-node transfer, boundary transfer. Most So those sort of,
here.
that will be there, but the communication methodology
Is taken care of by the compiler. When
how do you do it? Because GPU has to transfer to the CPU.
that compiler flags has to be set.
Exactly. So I am pretty sure it has to depend on the decomposition and all of that, which I think
We have to test it.
we have to
Basic example.
test it.
write a sample code because otherwise I cannot imagine it will be that one line.
In Param Shakti, that ICPH compiler, LLVM is installed, but it's not. We will fix and we will test it.
Yeah. No, so just two small codes. My suggestion is don't go into capital. First, get this thing working out correctly for a single thing, right? Allen Khan equation. Just make it run on single GPU, single CPU. Right? This I understand perfectly well. Multiple CPUs on a single node, multiple GPUs on a single node. Second, multiple CPUs between nodes, multiple GPUs between nodes. We have to see what type of parallelization and what type of codes change you have to. Okay. Once we have done that, I think we will have to come at a stage where we understand the architecture for you.
So API pop split type. Using that, we can create another local computer within the node.
See, for example, the topology of the MPI splitting, where you specify, how do you specify? All of that I need to understand.
You show you need to comp split.
Write a code economically.
Yeah. So three different codes. That's why I said single CPU, single GPU, multiple CPUs on the same CPU, multiple GPUs on the same node, and then internode. नहीं वो single GPU है but multi GPU नहीं था वो.
Then multi CPUs are
The kernel, electron kernel that is going to
उसका result ठीक नहीं आ रहा.
We can complete our job to the corresponding queue using the queue submit command. And we'll use an S dot parallel for lambda lambda function to do the jobs on do the calculations in the device.
What is the lambda calculation?
Lambda is a function. Lambda function which will inside which we can run the.
No, what is the lambda function?
Lambda function is when class has a call operator overloaded. So I can pass that equal to sign is there. Earlier, what I have to do, I have to create a array which I have to pass data directly to the GPU or CPU that I have.
Yeah, but where is the lambda function?
Equal to this equal to and then brackets and then curly brackets. So what the equal to sign in the square bracket does is it captures the variables, copies it to the GPU automatically.
Okay.
There are a few other methods available. We can define a kernel as a functor or as a bundle. So if you are defining our kernel as a bundle, we can pass
Multiple kernels at the same time. Multiple kernels at the same time.
Multiple kernels at the same time, and in that case, we can compile our kernel ahead of time. Usually, what SQL does, it's a
So here, if I understand correctly, H dot parallel for will run range. You are giving the range of the dimension of the system nx, ny, nz, and you are basically in that parallel for trying to go through the operation that needs to be done. That is this kernel, right?
It's a calculation function and this.
Okay. So in principle, the thing that you are not doing here, in contrast to a classical GPU code, is that you are not doing CUDA device transport of the data to the from host to device, computing there and then coming back. So that operation has been stopped.
Yeah,
That is done by the accessor.
If needed, I can use some point also.
What is this buffer now?
Buffer is a vector.
Why are you using buffer?
No, that is a vector. SQL vectors are called buffers.
No, but why do I need a buffer?
This is a local.
Memory storing.
This buffer is existing where?
It exists on the device.
No, but where is it existing? Device or the host?
No, there is nothing like that.
Huh? Then why do you need a buffer?
You need buffer to memory is allocated initially on RAM. When you define the accessor, you're defining the accessor, right?
Yeah.
Accessor to access that buffer.
Here you should.
Accessor to access that buffer will take care of the IO between GPU and CPU.
No, why do you need current access and the previous access? This is a
No.
TT plus one.
TP plus one. The important thing is that read only parameter. So if I define a particular buffer read only, in assembly there are particular read only fetch instructions. This gets compiled into that.
Yes.
I mean, still, it's not MPI.
No, this is not MPA. This is not.
It's not MPI. It's block.
It is 3D. Threads.
You call it as block.
We can create a block using empty range.
Okay. What did I want to ask?
Strictly MPI.
You can create multiple queues on the same device. Generate asynchronous workflow.
That is not the issue.
And the advantage of buffer is that the data transfer will be taken care by the runtime itself. If you are using data from the host, the data will be available in the host, and that will be ensured by the like SQL runtime. If it is if we are accessing in the device, it will be there. But we have to ensure certain things like we should not access the buffer at the host and device simultaneously or
Okay.
that we.
So you can mix time steps. All right.
So here, I don't see here, I mean, this is a kernel or what do you call it? So
This is the kernel only. It's a basic kernel.
you passing the whole system size, right? That NX and Y.
Yes.
You don't have any defined syntax to write any, kind of. See, the syntax in the single CPU or a MPL, what you write is a different, right?
Syntax?
In GPU, the way you write it in CUDA, it's different. You're passing entire system size and background SQL will figure out what batches it will send to each GPUs.
For that domain decomposition, we have to do separately.
No, what he's saying is even on a single GPU, how do you define the blocks and the threads and so on?
ND range available.
So now it is range. If you change it to ND range, you can provide that.
ND range will be basically block range.
Local size and total size.
So with the local size.
ND range. Local size is
Why don't you draw it by
total size is the total size. We don't size. Everything we don't.
Yeah.
Total size and block size.
Partial complete
No, now it's just doing range. The range is when each thread is executed parallelly. Then
Operations, the case of the that's
all for the local size.
yes, that it takes care of. You can explicitly via ND range.
Okay, so basically the kernel only.
Say something.
Basically all of the like CUDA and SQL, not almost all functions of CUDA or other GPU
Yes.
available in SQL, not directly. It has some kind of mask, but what it does in behind is almost same only.
So just Fourier transforms.
SQL,
No,
No, one MK.
you will have to write it yourself.
No, one MK. One API has MK libraries and FFT libraries
Oh,
that are universal.
So whatever.
one MK libraries will work in Intel CPUs and Intel GPUs. There is one man developed by Unified Acceleration,
One man.
which is available in all devices.
So you can demonstrate a FFT code on SQL. You to use the FFT code, SQL platform.
The problem I want to ask here, when you're taking a UFFT MP, so when you perform Fourier transforms of multiple GPUs, it shuffles the data.
Yeah, couple.
So when you want to manage the data in Fourier transform, you have to take care of the data format every
Yes,
time.
yes,
Right?
yes.
So how he is managing here, so that's
Well,
what
he's
I-
not written the FFT code. That's why I'm telling you to do it. Because
We don't do FFT.
Because I assume the FFT to transform it in multiple dimensions, they'll have to use the same transformation, which would be internally written because it's a multi-threaded thing. It will be having the same situation that you are using in CUDA. Yeah.
It has sort of introduction and atomic operations.
We don't want all the introduction. Don't read all of that. You will have to demonstrate it.
What does this computing offer?
That might be for the MPI operations.
I got a slide. Slide is titled "The First Step Toward Support for MPA Part
Communication.
on SQL Programming."
That can only be one thing. So run your code. You have a CPU and a GPU, no? Both. You need a GPU.
So you have a GPU emulator, no?
What do you mean GPU?
You know, Intel chips have a small GPU inherent in the
That is
CPU
a
that you
40
can directly use.
You have who has a GPU?
You have to install ICPX.
Wow.
Intel
Intel One API compilers are installed on certain computers, no? Intel One API. You have Intel One API? You have?
But this bit doesn't talk
Intel One
about
API. Intel One API.
beyond.
No, they don't. No one has it.
We're talking about data.
We have tested it.
Show them. Demonstrate. Seeing is believing.
No, we have run it.
I'm
on
not really
open
going to believe you if you don't. You can tell me anything. I'm going to believe you only when I see.
On derivation, we are saving on. No, we are doing.
No, telling and deriving, seeing. Step by step. 1 plus 2.
This is also so.
No, where is the GPU? It doesn't show in the GPU.
You cannot see a GPU.
I have to see.
How can you see?
You can show that you're running on the GPU.
Intel HPC.
You haven't. Even if you don't have the HPC one.
No, anyone is fine by himself.
Siddharth, you don't have one API?
He has Mac. So how can he have?
Nobody has one API. Cache simulator.
Intel One API.
You have one Intel One API?
They have
compiler?
CUDA people. Why would they have it?
No, here. Okay, there's one on my computer.
GPU code.
Huh?
I can compare GPU code in my system, but it don't run.
Okay, you have access to your computer LAN? Connect. I stop presenting before connecting. I don't know. I don't. We have CL info, no? CL info. Just run and check CL info. You might have a UHD emulator. That simplifies the task. It is going to be having similar.
Do data. This day, this target.
No, I expect some similarity with.
Good.
Yes, yes, yes.
There is one more computer you can add to CPP, which also supports there are two companies. There was one more called but acquired by Intel. They were doing well.
So if I'm using a GPU,
Schedule control plus.
if I'm using an NVIDIA GPU, then I have to set a flag for target GPU. So it will compile for
That's okay. A little bit more also.
Okay, so that inform what is the target.
So,
PTX, it will convert to PTX.
NVIDIA.
so there's something other than NVIDIA PTX?
Even the AMD ROCm. Don't you have to provide.
But then not PTX, it is some other.
It's done, no? 1 year period. Set variables is done. Come clear, make it come up.
Control L, you put Control L. Even in the middle of a command, you put Control L, it will clear.
So he's combined and,
Run it.
Scroll down. That is one of the first things you'll encounter in segmentation.
so I have written the code such that we can pass arguments like index number of index ny and time steps in.
You're running where?
It's running
Your machine.
on my machine.
You go to Chennai.
Yeah. Okay. So this is run on the RTX. Run it on the CPU now. Which CPU are you going to use? Run your 128 CPU, no?
Yeah.
No, 128 node CPU. Core
The
CPU.
system is currently off.
Is that done? Can you connect to the 128 nodes to our 128 CPU? Yeah.
Yes.
Huh. I want to see the time.
So this is a very small code, but it doesn't matter. That's a.
You have a single link CPU times.
So this, though it is changing, we can also change it from some flag, right?
Yes. You can.
Fine.
You have to default.
Finally, this will go into a make file, so don't worry. Finally, this will go into a make file.
Yes.
You can do it, if we do make it virtual, you can make the queue inside the virtual function. So what will happen is at runtime, you can select whether you want CPU or GPU, once compiled you do. But the compilation won't be that efficient. Because they are giving the article.
It's better to do it some.
Compile time is better,
Yeah.
because we don't mind compiling again and again.
Yeah.
Okay, let us try this out.
Or you run it on your CPU here only. Here only.
No, the same machine. Let us.
Okay. What is the configuration of the CPU? CPU configuration in that machine?
Yeah,
3700. Intel i7
i7. Desktop.
Yes. How many CPUs does it have? Cores? 16 or 32? 16.
CPU, you don't need to tell what is the time.
Why target just
Yeah, for every target we can specify. In the core also we can write the default selector. So if we specify the target at the compare time, it will.
So 16 things are running faster. 16 CPUs have executed faster than the GPU.
Which is very.
This is not good. Bro. हाँ? जब हार गए हो तो फिर
CPU लोग नहीं मानते हैं.
all that you have tried to do.
See, anything we have a new code development, we should think of. So it can be imported.
Oh, it alone.
So
You don't really you have to redo the
These are
whole,
going to
but
do so much.
that's the best thing. No?
That's why we are thinking very soon we'll replace.
Thousand only.
Understand.
Huh? That's what I'm saying. Do it 1,000 of those.
The documentation. The extent there is-
The number of streaming codes in that thing is limited. So that's why it's not. The RTX 4060, I think is around 6,000 streaming. I understand 6,000 streaming codes. You will already populating with 100 cross 100 itself is coming close to that.
Still doesn't give me once,
Also, the each code is faster. No? That's why.
Clock speed is faster.
Point 37. Chi. Huh? Huh? GPU. Huh? That's the 10 times more time it took. Nothing, no more argumentation. CPU only.
Next year is coming.
Huh? This will also GPU.
I have
Only all code, but you have to compare with GPMP. Then we'll go.
So with it, I can combine, I can prove it with my course.
No, with FFT, right? FFT is
FFT obviously slower. That's why we are using yours.
No. That AMD is giving 128 cores for less cost.
So good, CPU wins.
No. You should have SQL win because SQL will run on anyone you like.
See, that is why I wanted them to show.
Actually, I am using global.
It's okay, I understand.
Local.
No, there are things that can run on the faster on the GPU. You have to curtail your, make your code in a way that.
So here, I don't know if this is going across. It would have actually is not an open. It's a royalty. So tomorrow, if you're making money, they can come and say, give us some share. And, Apple has started OpenCA, which is a free platform, but it is Kronos Foundation. Apple has its own proprietary language called Metal now. So when everybody is going